Hello and welcome to Unit 4, Conservation of Energy. In this lesson, it's Lesson 6, Conservation of Energy with some non-conservative values, meaning that there is work at play in these questions. This is example number 2. It's 2 of 2 in Lesson 6, so the last example of this series. And we have we've got a bit of a bigger problem here. I wouldn't say this problem is much harder, but there's just a lot going on in this diagram that I'm going to have to explain before I really start solving here. Alright, so what we have going on is we have a block that starts at rest. This block weighs 45 kilograms. It's going to be both pushed up the hill by some applied force, but also there's a fairly large force of 320 newtons of friction that's also going to be applied along the way. Along the way is a 110 meter stretch up a slope, and when it reaches the top it will be 39 meters high. Now when this block finally reaches the top of the slope, all we know about it is that it has a final velocity of 27 meters per second. Alright, now the question is asking us to find our force applied. Okay, so I don't think that should be too incredibly challenging, but let's give it a go, why don't we? Couple things that I want to work out here. I'm going to start with our basic conservation of energy with non-conservative forces formula, and we're going to say that the initial mechanical energy, so energy mechanical initial, I'm going to leave this a little bit shorter because I want to keep my page a little bit more free. There's a lot of writing to go on in this question. So initial mechanical energy is not equal to, plus our work function. So our work function due to some forces. Maybe I should have started with my work forces first, but you know what? We'll get there. I'm going to say that this work function is due both to our force of friction acting downwards and our force applied acting upwards. So I think hopefully you can see that we're going to be dealing with the work done by the net force here. And I'm going to come back to this very briefly. As soon as I'm done with this step, I'm coming back to this. But I'm going to say that this is the work done by our net forces. Alright, then that is going to equal our energy mechanical final. Okay, now down here I'm going to deal with this work net. This right here, bringing it down here, and we're going to talk about this. So, just like when we have force net is equal to the sum of all the forces, so force net would be equal to force applied plus force of friction. Well, since work is force times distance, we could say that work net is equal to the work done by the force applied. So maybe we can say work done by applied force plus the work done by our friction force. Because essentially all we're going to be doing is multiplying each of these terms by the distance traveled. Okay. Right on. So, with that said, we've got a bit of writing ahead of us. Let's talk about what we have going on up here when we break up this network into two separate pieces. Okay, our initial energy. Let's figure out what we have for mechanical energy initial. We have no springs, we have no height, so potential energy 0, and this block is at rest, meaning we have no kinetic energy. We have no energy in this block. This mechanical energy initial is one big goose egg. Okay? Plus our work net. Our work net is going to be the work done by the applied force plus the work done by the friction force. Keeping in mind friction is going to be backwards, but that will get taken into account when we finally expand this out. So let's call this work applied, work done by the applied force plus work done by friction. Okay, so there's our work somewhat expanded out. And this is going to be equal to our final mechanical energy. So at the top, I think we see we're going to have quite a large value for mechanical energy. We have both potential and we have kinetic. So let's say energy, kinetic, final, plus energy, potential due to gravity, final. Alright, the reason we have kinetic energy is because our object is moving. If you have mass and velocity, you have kinetic energy. If you have height, you have potential energy due to gravity. Right on, so let's further expand this now into each of their individual formulas. Okay, this step right here, really the least amount of writing is the hardest step of the whole problem. It's identifying each of the pieces. So if you can get to here, you can finish this off easily. Okay. So, the 0 I'm not going to rewrite, but the work done by the applied force, we'll say that work is equal to force, and this is the force applied, times distance, times cos theta. And this is a lot here. Yeah, I'm going to start putting these things in brackets, just to keep this a little bit more clean. Plus work due to friction, so this is going to be force of friction times delta D times cos theta, okay, is equal to kinetic energy and potential energy. Hopefully we're fairly good at this by now. This is 1/2 times mass times velocity final plus mgh final. Alright, we're at the point where we can just put numbers in and finish it off now. Alright, be warned that this is going to take a lot of space if you want to write it out on one line. I'm actually going to start it way over here. So, change my colors too. And let's add some numbers in here. The force applied, the very first term is what we don't have. So force applied times displacement of, it's moving along this axis, so 110 meters, times cos of 0 degrees. There's 0 degrees difference from the direction we're pushing and the direction it's moving. They're in the same direction, so no difference. Okay? Cos 0 works out to +1. Okay, this is gonna be added to, and honestly I want to stick this in some brackets. Gonna add it to force of friction. We have that value. This is 320 newtons times displacement 110 meters times cos of 180 degrees. Okay, I explained this cos 180 in the last video because what's going on is our motion is up the hill, our force of friction is acting down the hill. They are opposite directions. They are 180 degrees apart from one another. So this cos 180 is going to give us a -1 value here. Alright, that side's done. You can say this is equal to 1/2 times the mass, which is 45 kilos, times the velocity. I didn't put the squared on here. Alright, times the velocity, which at the top, the final velocity is 27 meters per second. You can square that one, and then add in mass times gravity times height. So this is going to be mass 45 kilos times gravity, 9.81 meters per second squared. Alright, and I'll do this one here, I guess. Times height, which is 39 meters. Alright, couldn't quite fit it all into one line, but that's okay. We're going to do some major solving here, and I will solve for a couple intermediate bits. I just solved essentially all the terms on each side, and I end up getting 110 times applied force minus, because this value turns negative because this cos 180 is a negative 1 value. So this is negative 35,200. That I believe is going to be in joules, is equal to, over on this side, I get 33,619.05. Alright, we're going to flip this over, and I get 110 force applied is equal to 68,819 joules. Divide both sides by 110, and we get an applied force equal to 626 newtons. And that is the final answer to this question.